Hello everyone and welcome back to the Kohi Game Engine series. Today we're going to be tackling multiple render passes. I would like to take a quick second and thank the supporters of the channel, Eearslya, Wensheng, Caden, and Joel. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. Okay, so I know we have a lot of things on our roadmap that we want to get knocked out, but I got thinking about it, and I think we actually need to take a step back and make a pretty major change that's going to be super important for our architecture going forward. And that is, we need to have a concept of multiple render passes. So if you recall, there is a construct in Vulkan called renderpass. So a render pass basically takes a series of attachments and forms a bunch of operations as defined by a pipeline and a series of commands and outputs to images attached to a frame buffer. And so right now we only have one render pass, and that is basically drawing all of our geometry in the world using our depth buffer and our color attachment to render our geometry on the screen. And that's all well and good. But when you have more complex systems that need to do more than just render a scene, you're actually going to wind up needing multiple render passes. And so one of the first things that we're going to need a render pass for is actually our UI system. And UI is something that I don't want to put off too much longer because it is a very complex and quite verbose thing to implement. And so it's going to take a little bit of time to actually get one up and running. But our engine needs to be prepared to handle that first. So why do we need a separate render pass for that? Mostly in part because the way that UI is typically rendered is vastly different than the way that geometry is rendered for a three-dimensional scene. So typically when you render a scene, you render out your models, you render your things like skyboxes, terrains, water, and then once you have everything rendered out to the scene, you go ahead and you apply some post effects. Those post effects might be, say, bloom, for example, or HDR. All of those things can actually be taken care of in a single render pass. But UI, typically speaking, is very different in that UI is typically two-dimensional. There are games that have three-dimensional UIs, but we're not going to be implementing one of those, at least not right off the bat. But at least the system will be capable of handling that once we get to a certain point, right? But my point is, we actually, at least in our case, don't need a depth buffer. So that's already one difference between our typical world rendering and our UI. We also, since we aren't using a depth buffer, we're obviously not doing any depth testing. And so the pipeline configuration is different for those things. The amount of attachments already is different. And so already that means we need a new render pass and we need a new set of frame buffers, okay? And so our system is going to be a 2D UI system, at least for now. And we're going to have what we call built-in render passes, where we'll have what we're going to call a world render pass that renders our three-dimensional world. And then we're going to have a UI render pass, which renders a 2D UI on top of that, okay? And so we're going to have our world render pass that goes first, writes out to our swap chain images, and then also writes to the depth buffer for depth testing if we need it for additional subpasses or something along those lines later. But then we're going to have our second pass that contains the UI, which is also going to write to that same set of images, which are going to be referenced through a different frame buffer. Okay, so I hope all that makes sense. Once we actually start to get in here and mess around with the code, I think it'll make a lot more sense. So actually, before we do any of this, I'm first going to add one more texture to our collection. And this is just going to be this orange lines 512 texture. And if I open this up real quick, I'll use just photos is fine. This is a texture that allows us to see that the whole thing is mapped onto the screen, as well as that it's oriented correctly, right? Because that's going to be super important to verify that. It's a little harder to tell with some of the other textures. So we're going to use this texture to sort of help us out with that. Okay, so I've gone ahead and pasted that in there. That will be available in the repository when this video releases. Okay. All right, so with that, we will now start going through all the changes that we need to make. And we're actually going to be touching a lot of files. And some of these changes are more significant to some of these files than others. So I'm going to basically breeze through this as quickly as possible so as to not make the video take too long to actually get through, okay? So with that, there are a couple of changes that I want to make that simplify our architecture a little bit and get rid of some things that we don't actually need. One of those first things is going to be the Vulkan fence, right? So if we take a look, actually let's look at the C file. So if we take a look at this, all the Vulkan fence really gives us is in the type itself, actually, we have the VK fence, which is the actual handle to the fence, and then just an is signal boolean. And we don't actually really need this, right? We can actually get rid of this because we actually don't need to know or care about the is signal property. And I know a couple of you guys have asked about this, and it's been a long-standing issue that I've wanted to get resolved. So I'm actually going to delete that type. And I'm also going to come in here to Vulkan fence and delete the H and C files because we actually don't really need these, right? All of this logic can actually be split out. The only thing that we don't necessarily have an exact copy of is this logic here, but we actually do have our Vulkan utility methods that can look at the result and actually give us the error code. So we actually don't need this either, right? This whole check to see if is signaled before resetting fences, we don't need to do that either. We can just reset the fence. If the fence is already signaled, this is just going to proceed, right? So we really don't need this check either. So this is going to go bye-bye, okay? Which means that in our back end, we're going to have some errors now, right? So the first thing I'm going to do is actually get rid of the Vulkan fence.h at the very top. And we're going to come down here and actually we have our context in-flight fences, which is a D-array reserve. And this is actually using our Vulkan fence type, right? So we actually need to go to the definition of that, and we need to replace these things. So while we're in here, one other thing that I want to go ahead and change is we're never going to have more than 2 in-flight fences at once, right? So there's really no need for this to be a dynamic array. So what I'm going to do is I'm going to change this to VK fence, right? Get rid of the pointer and set it to be an array of 2, right? Because we're never going to have more than that. Okay, we might only use one of them. Technically, it's a little bit of wasted memory, but I'm not really worried about it, right? It's such a minute amount, it really doesn't make a difference. The other thing that we have here is this double pointer, which is used to hold pointers to fences that are owned elsewhere, which would be here. Okay, so this, instead of being a double pointer, is just going to be a single pointer to a VK fence right now. Okay, and that is also going to be a hard-coded array, but there's going to be 3 of those, right? And these are going to be 1 per frame, right? So this will tell us, this will be indexed by image index, okay? So that is that. So let's go back to our back end. That means we can actually remove this line of code because we don't need to D-array reserve that anymore, okay? Down here, the images in flight, same thing. Don't need to do that. We just zero them out, okay? And then in our destroy here, we have D-array destroy. We can get rid of both of these, right? Because they're no longer dynamically allocated, so they don't need to be released either. Next, we have our VKQ submit, and this is taking the context in-flight fences, and then it takes the handle to that, right? This should just be minus the handle bit, okay? And that's because we're now using the VK fence, which is what this expects, okay? All right, let's see. I'm just going to do a quick search for Vulkan fence. Oops, if I could spell it right, just to see where else this is actually referenced. So again, in our Vulkan backend, anything that's calling Vulkan fence create, we now no longer need to do that. So in this case, we're actually going to remove this code. And we want to remember that we need to create the fence in a signaled state, right? So we're going to go ahead and create a fence create info with the signaled bit set, right? And we'll go ahead and call vk create fence, okay? So that's that. Vulkan fence destroy is pretty much the opposite of that. So instead of this call to Vulkan fence destroy, we're going to go ahead and replace that with vk destroy fence, right? Which returns void, so we don't need to check the result of that, okay? So that is that. Other than that, we have a wait that we need to do. So this one was basically using our Vulkan fence wait. I'm just going to actually replace this as well as the actual warning message, which really should have been an error, with something a little bit better and more descriptive. So what we're going to wind up with here instead is we're going to take the result of vk wait for fences, right? It's going to pass all the same parameters as before. However, we're going to say if it's not a success, go ahead and write an error message, but this time let's actually spit out the string with the extended message as to what actually happened, okay? So if we ever run into any issues there, we'll have a little bit more detail on that, okay? And then we also have another fence wait, okay? And this one we're going to treat as a fatal error, right? If we actually have a fence in this particular slot and it's not null, then we're going to go ahead and wait on fences. And again, if we get an error about that, we are going to go ahead and spit that out. And this is going to be treated as fatal because if something happens here, that's definitely a really bad thing and we should not try to recover from it, at least for now. The only other thing is the reset, which actually, believe it or not, is also just one line of code. So this guy here is going to be replaced by this, right? As you can see, having that file there really wasn't providing us that much value. It wasn't really hiding that much code. So I think it's just a lot easier and more straightforward to deal with it this way. Okay, so that's the special Vulkan fence type gone, okay? The next thing I want to do this with is the frame buffer, right? Because frame buffers are kind of the same thing. So if we go in here and look, there's a little bit more code here. But the frame buffer itself really isn't storing a whole lot of information that we care about, at least right now, okay? And if we did care about it, we could always store it in a different manner. So the Vulkan frame buffer right now keeps a handle, keeps an attachment count, as well as an array of the attachments, and it also keeps a pointer to the render pass. All of these things don't really matter after the frame buffer is set up and complete, so we don't really need to track this or keep it, so I'm going to delete this as well. Which means I'm also going to come in here to Vulkan framebuffer.h and remove it, as well as here. Okay. You'll also note that the Vulkan types is now throwing an error because we have our frame buffers here. Instead of dynamically allocating an array, again, we're only going to have 3 of these because it's 1 per frame, right? So we're just going to call this frame buffers within our Vulkan swap chain is always going to have 3. Again, even if we don't use 3, it's not really that big of a waste, okay? All right, so that is the frame buffer file gone. So next we need to fix Vulkan backend because it was using this file as well. So I'm going to go ahead and remove frame buffer here. All right, and we're going to basically just resolve these errors one off, right? So right here, we're actually reserving that array. We don't need to do that anymore. And then we're calling regenerate frame buffers. We're actually going to be refactoring that, but we'll come back to that. So that's the first one. The Vulkan render pass begin is actually looking for the VK frame buffer itself. This was returning the handle of our old object. So I believe all we need to do is actually just remove the handle from that. I think that's actually all we need to remove from here. So let's actually do the same thing we did last time. Okay, we're not using the Vulkan frame buffer anywhere else. Okay, So we've gone ahead and gotten rid of everything except the create and destroy. All we're going to do is replace this call to destroy with vk destroy frame buffer, right? And it's just going to go ahead and take care of getting rid of that for us. And then we also have another call here that does the same thing when we need to go ahead and regenerate the swap chain. So we're going to go ahead and do that as well. All right, and next we have our frame buffer create call here, okay? And this is the function that I was saying that we're going to wind up refactoring, because this is actually making some assumptions, right? It's making an assumption that we're going to want 2 attachments for every frame buffer, which is not going to be the case, okay? But for now, we're just going to go ahead and sort this out, okay? So the first thing that we're going to do is create an array of image views, which is for our world frame buffer, which is the only frame buffer we have right now. That's what we're going to rename it to. For that, it's just 2 attachments. So one is the swap chain image and the second one is the depth attachment. So we want the views for those. Here's our frame buffer create info, right? So it just says how many attachments we have, what render pass we're actually going to be using. So we're actually not going to take this parameter. We're actually not going to take any of these parameters anymore. Our attachments are here. The width and height are set to the frame buffer. Width and height, our layers is 1, okay? And this is bleating because we have something here called world frame buffers, which doesn't yet exist. So with that, actually, let's go ahead and go to our context type. And this is going to be back in Vulkan types, because this is where we are going to add our frame buffers, right? So we actually need to add right above memory index, find memory index rather, we need to add our second set of world frame buffers. So what we're going to do is we're going to, our first render pass is going to point to these frame buffers here, and our second render pass is going to point to the swap chains frame buffers, okay? So filling all that in, that is what we are doing here, okay? So this is the first render pass. So this is the first set of frame buffers, and this code right here we'll go ahead and clobber and replace with the second set of frame buffers, okay? And these are going to be connected to something that we're going to call the UI render pass. So I'll come back to that in just a second. So in this case we have one attachment, which is just our swap chain image at the given index, okay? And then we have our create info here. We attach our new render pass to that. We have one attachment. Here's the array of those attachments. Width, height, layers equals 1. And then we go ahead and create the frame buffer. And this is going to point to our context swap chain frame buffers sub I, okay? So these are what the frame buffers look like, which ought to give you some clue as to what the actual render passes themselves will kind of look like, right? So our standard rendering that we've been doing so far will go to this one. Our new UI layer, or our UI pass rather, will go to this one, okay? So with that, we probably ought to go ahead and put in the UI render pass in our type. So I am just going to go ahead and go to that definition and put in a render pass here for us, okay? So this is our second render pass, this is our first render pass, okay? All right, and now that this is done, we actually don't need either of these things anymore. And we'll go ahead and get rid of that to-do because that doesn't really apply anymore, okay? So we do want to make these things dynamic, but at least the configuration is all here and visible, okay? All right. The other thing that I want to do as a small optimization is I'm going to go ahead and take the swap chain image count here and reference image count in the loop so we don't have to keep getting that, right? And that pretty much does it for regenerate frame buffers, at least for the body, right? As far as our signature, we actually do not need any parameters anymore. So we're going to get rid of those. We're going to go to the top to our forward declaration, and we're going to get rid of those, okay? And now when we call regenerate frame buffers, we are not going to pass anything because it has all the information it needs right in the function itself, okay? And that's all of it. Okay, So with that, we have our regenerate frame buffers, but you also remember we had this destroy frame buffer that only took in our initial frame buffers, right? So we actually need our other frame buffers to be included in that list, our new ones rather. So what we're going to do is just above that, we're going to include our world frame buffers in this destroy call, and I'll just go ahead and look for the next one and do the same thing there. So that way we are sure that we are destroying our frame buffers properly. Okay. I believe that is it for frame buffers. So let's go ahead and just build real quick for a sanity check. In fact, I think I'm gonna have to clean and build. Yeah, because we don't have, see, our Vulkan backend object is still referencing that frame buffer.h. Let's check that. It is not, but I believe we actually need to go ahead and clean and rebuild because we deleted some objects which are now trying to build and shouldn't be. It's a good idea to do that once in a while anyway. Okay, so we built successfully. We should be able to run, and then we'll actually see here that we have an invalid render pass because we actually haven't set these render passes up correctly. So this is actually kind of what we expect. So the next order of business is to actually enhance our render pass to make it a little bit more configurable, and then create our second render pass. Okay, so I'm going to start with adjusting the render pass first and adding some things to it to make it a little bit more configurable. So we'll go here to Vulkan render pass H, and we actually want to be able to describe what type of clearing operation we want, right? Because if you recall, the way that the flow of this is going to work is those swap chain images are going to be used in the first render pass and the second render pass. So for the first render pass, we actually do want to clear those images. We want to wipe the data clean and start over. But in the second render pass, we don't want to do that. We want to load the data that's already there for that render pass. And so this kind of brings up the need for us to be able to granularly control what type of clearing we do in a render pass. Thus, we have a type def for render pass clear flags, where the default would be none. We can provide a color clear flag, depth, or stencil. These are all powers of 2, so they can be ORed together, right? So you can combine these flags to actually to use all of them or some combination thereof. Okay. And so our render pass create actually needs to know this ahead of time. So we're going to add a new property after stencil, which is a U8 clear flags, right? Because that's what these are. These are just 8-bit integers, essentially. Okay. So we have this clear flags here. And then we also want to indicate whether or not we had a previous pass and whether or not we have a next pass coming after this render pass, right? Because there are certain things we're going to have to adjust if those things are the case. And then one other thing that I wanted to mention and sort of update that I sort of mentioned very early on in the series is we didn't have the math types to be able to represent our render area and our clear color. And so now we actually do. And I want to go ahead and replace these things with the proper types. So I'm going to clobber these floating points and instead use vector force. Just kind of cleans this signature up a little bit, right? Okay, and that is all the changes in the surface for render pass create, okay? And render pass in general, actually. So I'm just going to copy this signature, go to the C file here, and I'm going to go ahead and overwrite this one, okay? And what we actually need to do is the render pass itself is actually going to need these same updates. So if we go to out render pass and the render pass type, we have here the X, Y, W and H, RGBA. We're going to replace those with render area and clear color respectively. Okay, and we're also going to store off the clear flags as well as these two flags as well. Okay, so let's go ahead to the type and we'll go ahead and Whoops, that should be a semicolon, not a comma. We'll go ahead and add these things here so that we can store that, okay? And again, these should be semicolons, not commas. Okay. And then what we can do is this operation in here becomes a lot leaner, right? So we can get rid of all of this and just set the clear flags, render area, and the clear color, right? And we'll also go ahead and copy over the has next pass and has previous pass. Okay, so we'll copy all those things over so that they're stored. So this is a lot neater than having to deal with all those separate numbers. All right, so there's a number of changes that we're going to have to make in this file in addition to what we've already done. So let me get rid of this console, whoops, and get rid of that one and that one. Okay, so first thing is attachments to do make this configurable. I'm going to leave that there because this is not going to be completely configurable, right? Because we're going to add a little bit of enhancement here, but it's still not going to be perfect, okay? First thing I'm going to do is make this non-const and set this to not use a variable length array, right? So we're just going to hard code that to 2. Again, that's why I'm leaving the to do here, right? So this we're going to basically increment as we attach the actual attachments, and this is going to be the maximum length that of things that we can attach, which for now we only need 2, so it's fine. So the first thing that we need to do is for the color attachment, we need to determine whether or not we are clearing the color attachment, and we do that by taking the out renderpass clear flags, anding it against renderpass clear color buffer flag, right? And if that and is not equal to 0, then that means that it has been set, right? So that'll flip this to true. And the reason we want that is down here for the load operation. Right now, we're explicitly calling clear, but we don't always necessarily want to do that. So if we are calling do clear color, then we do want to use that. If we are not, then we want to load, right? And so this is what makes that determination there. Next, for the initial layout, we actually want to be a little bit fluid with this as well. So right now we're just hard coding that to undefined, meaning that the image layout or the contents of that are undefined, and since we were clearing it, we didn't care. But now where we're going to be potentially loading that in from a previous render pass, we do potentially care. So what we're going to say is if coming from a previous pass, then we should already be in VK image layout color attachment optimal, and that's for this attachment. Otherwise we'll use undefined. So if we have a previous pass, meaning this is set to true, then we'll go ahead and use the layout color attachment optimal. Otherwise we'll use undefined as before, okay? And as you may have guessed, since we're talking about output here, that means that the final layout also needs to change. And so the final layout right now is just representing what is optimal for presentation. But this is not always necessarily what we're going to need. So in this case, if we are going to another pass, then we want to use this color attachment optimal, which is what we're checking for here, right? So if we have another pass, we're going to use that instead. Otherwise, we'll go ahead and use present, because if this is the last render pass in the queue, then that means that likely the next thing that we're going to do is present. So this is the update for that. Next, we have this attachment descriptions that's hard-coded to a 0. We're going to do attachment description count, and this is to make this is sort of a first step in making things a little bit more dynamic. So we're going to attach that and then increment the attachment description count, right? Just makes things a little bit more dynamic. So at this point we'll have one attachment because we're not conditionally attaching this. It's always getting attached, but if we ever do conditionally attach this, that logic is already in place. Okay, so next we need to handle the depth attachment. And this is one that's going to be attached conditionally. So just like we figured out if we're going to do the clear color we're going to figure out whether or not we need to clear depth here. And for that, we're just going to check to see if the clear depth buffer flag has been set. Okay. If it has been set, then we're going to go ahead and attach this. If it is not, then we're not. So that means that we need something here to check that condition. Otherwise, we are not going to go ahead and attach it. So let's see. Right down here, after we make the depth stencil attachment, we are going to put our else. Okay. So if we're clearing the depth, that means we're also using the depth. And we probably, again, will have something else to determine whether this should be attached, but for now, we'll switch on that, okay? And so if we're clearing the depth, that means that we're using the depth, so in this case, that's fine. As before, we need to do a check to see if we are clearing the depth attachment. Then we need to go ahead and call or use the load op clear. Otherwise, we should use the load op load, right? So we're just going to do another check in here for do clear depth, and if we are clearing, then we're going to clear, otherwise we load. Okay. I do realize that this will never be hit because of this, but this is going to wind up changing at some point, so don't worry too much about that. Okay. Next, similar to what we did above, we're going to get rid of this hard-coded 1 and use attachment description count, which at this point will be set to 1. Okay. And then we'll go ahead and increment that on the next line. If we don't use that, then we go ahead and we want to zero out that attachment description. So actually, instead of a 1 here, we should say attachment description count. We should just say attachment description count, right? Because we wouldn't have incremented that in that case. So if we're not using it, we want to zero it out so that Vulkan doesn't think there's something there, and then set the depth set stencil attachment to null. Okay, so we only attach this if this is true. Okay, so we're almost done with the changes in here. The last bit of changes we need to make revolves around this stuff because these X, Y, W, and H no longer exist. So what we're going to do is replace this offset with this code, which looks at the render area that we added to the render pass, X, Y, Z, and W. So this is not to be confused with before we had width, or W, which was representing width. That is not the same as the W here, which is now representing the W component, which is the fourth component. Okay, so Z basically doubles as width, and W doubles as height in this case. Okay, so we're going to swap that out, and then we're also going to start off by setting our clear value count and our clear values to 0. And this is because we might not clear anything, right? So we're going to default to that. Okay, and next we're going to go ahead and do a check. And in fact, actually, I can get rid of this whole block right here. So next we're going to do a check to see if we're going to clear the color, right? Because if we're if that flag has been set, then that means that we need clear information for that. Okay, so I actually forgot a bit here. Right above that, we need our clear values right here, right? I forgot to add that in there. So we have just this array of 2 clear values. We zero out the whole thing, right? So here, if we are doing the clear color, then we're going to go ahead and clear out the first one, right? We're going by this clear value count, which is set to 0, and then we increment that clear value count to 1, okay? And then similarly for the depth, we're going to do basically the same operation, right? We check the flag. If the flag has been set, then we zero out the next entry in that, and then we go ahead and copy over the depth, and then we check the clear stencil, right, and see if that is actually set, and if it is, then we go ahead and set the depth stencil value to either the stencil value that was passed in during creation or 0, okay? And then we go ahead and increment this again. And finally, we go ahead and come down here to the bottom. So we set p clear values conditionally by checking the begin info clear value count. If this is greater than 0, then we use clear values. Otherwise, we just set it to null, okay? And that is the extent of the changes to the Vulkan render pass. Okay, so now we can come back to our Vulkan backend and update our render pass create methods, right? So right now we only have one of these, right? And this is for our world render pass, right? So we take the context, the main render pass, and then we have this here, which is now a vector 4, right? So we can actually just simply convert that to a vector 4 by doing this, right? And that uses vector 4 now. And then we can do the same thing here for the color, right? So this is just a dark blue color, right? So same thing as before. We'll leave our depth and stencil as they are. And then in this case, for our clearing, which is the next thing that we need to add, our clear flags, we need to OR together everything, right? Meaning we want to clear color, we want to clear the depth buffer, and we want to clear the stencil buffer, okay? So we want all of those. And then the next two fields are has previous pass and has next pass, so that's going to be a false followed by a true, right? Because this is the first pass, but there is a second pass. Okay, so as you might have surmised, we are going to have a second render pass. So we need a second Vulkan render pass create called, right? And this one is largely the same as the one before. We're this time pointing to UI render pass. We're passing the same rectangle for the render area. We're passing black as the clear color, which is actually fully transparent as well. This doesn't really matter, it's not really used because we're not clearing it, but we have to pass it anyway. Same depth and stencil, again, they're not really used. And then we're going to pass here render pass clear none flag. So here we're clearing all of them, here we're not clearing any of them. And then in this case, we have the opposite for the Booleans here. So we do have a previous pass, but we do not have a next pass. Okay? So that is that. So obviously we're creating a new render pass. That means we need to go ahead and destroy a render pass as well. So right here above our Vulkan render pass destroy for main render pass, we're going to do the same with UI render pass. Alright, and if we go down here a little bit, we've got a couple of errors here. We have our main render pass W and H. Those no longer exist. Those are the render area Z and W. So we're going to go ahead and replace this with that. Get that updated. I believe we actually have another place where this is the case. Yes, we do. So again, we're just going to update this to use our render area. We have our frame buffer destroys here. We'll go ahead and also update this as well to use render area. Okay. I'm also going to put a comment here just to say exactly what that is doing. One quick change that I want to make too is here in our create buffers, I actually just want to add a couple quick notes here as to what that's for, because we're eventually going to be having more of those as well. Okay, so that should do it for our render pass. So let's go ahead and build, and we'll run. And you can see here that we're still getting some errors. So we'll need to make some adjustments on that, right? And this is to be expected because we haven't actually hooked up both render passes yet. Okay, but we get to that point before it fails, so we know everything is working as expected. This is expected. So the next thing we need to talk about is right now in our begin frame, we've sort of got this hard-coded path of beginning our render pass, and then in end frame down here we end the render pass. And this is all well and fine for what we've been doing so far, but what if we have multiple render passes, right? That we don't necessarily want to be nested in this way. This isn't really something that is going to be very flexible. So we need a mechanism to be able to start and end render passes in any order, really, on demand, right? And so we're going to get that by going to our Vulkan backend, and right below our backend end frame, we're going to add two new methods, one to begin a render pass and one to end a render pass. And we're going to pass the backend, and then we're going to pass a render pass ID. So our render pass ID is just a U8. So where exactly does that come from? Well, if we go to render types INL, we are going to define some built-in render passes, right? And these are ones that are known to work a specific way and are only configurable to a point. Eventually, we're going to have a graph where you can build your own render passes, but these are ones that are actually built into the engine, okay? We're going to have one called world and one called UI, as I've mentioned before. These are the codes that we're going to pass into that method to be able to tell us which render pass we are beginning and ending, okay? Right here. So since we have these, we'll go ahead to this method, and we'll go ahead and add these right below end frame. Okay. And what that means is we're going to go ahead and get rid of this render pass end, and we're going to get rid of this render pass begin, right? Because that is no longer part of the begin end frame cycle. We'll begin a frame, then we'll start the render pass of our choice, and then we'll move on from there, okay? And so begin render pass. So the first thing that we're going to do in this is just take a couple convenience pointers, right? We're going to take a pointer to a render pass, we're going to default that to 0, same thing with a frame buffer. And eventually the way this is going to work is we're going to choose a render pass, assign it to these, and then start that render pass using this command buffer, okay? So the way that we start that is actually pretty straightforward, right? So we have our render pass ID that's passed in here. If that is render pass world, then we set our render pass to the address of main render pass, and we use our world frame buffers, okay, at the appropriate index, of course. Otherwise, if it's the UI, we go ahead and use our UI render pass and our frame buffers at the image index, okay? And if for some reason we pass something else, we're going to throw an error here saying, hey, we don't recognize the render pass ID that was passed in. Eventually this will be enhanced to also look for custom render passes, but for now we're just going to throw an error. So once we've chosen that, then it becomes as simple as just calling Vulkan render pass begin and passing the chosen render pass and frame buffer, okay? However, there's one thing that I haven't talked about yet that we are going to need to do as well. And one of the reasons I'm doing this right now is because we need to actually create another shader. Because eventually our material shader is going to do a whole lot of things with lighting and whatnot that we don't need from our UI shader. And so our UI shader is going to wind up looking remarkably like the material shader looks now. And so I think this is a good opportunity to go ahead and split those things apart. So that's what I'm going to do. So one other thing that we need to do is, instead of calling Vulkan material shader use all over the place, we are actually going to call a different shader, which is a Vulkan UI shader, that we are going to create in a little bit, right? So we haven't created this. This is going to bleat about it until we actually do, and that's fine, okay? All this means is that we are just using that shader for the UI render pass, and we are using the world shader for the world render pass, okay? And then once we've done that, we get to the end and we return true, okay? So only if we fail here do we return false. Great. So our end render pass basically does mostly the same. So it picks a render pass. This time you don't have to pick frame buffer because we just have to pick a render pass to end, right? We also don't have to do any shader using or anything like that. So this is pretty simple, and I feel like it's pretty self-explanatory. So that is to end that. So the only thing that we have to address now is this Vulkan UI shader use. So let's go ahead and adjust that. But I think before we do, there actually is one change, a couple small changes we need to make to our graphics pipeline. Because right now our graphics pipeline is making some assumptions about the shader that's going to use it, and that's not always the best thing. And so we need to start making this a little bit more configurable, and it's not, again, going to be completely configurable right out the gate. We're going to make this more configurable as we need the ability to flip switches, right? So the first thing we're going to add is something called stride, and this is basically the amount of each element of a vertex, right? So a vertex 3D right now has a stride of the number of bytes for a vector 3 and a vector 2 for position and texture coordinate, right? And then we're also going to pass something else after isWireframe called depth test enabled. And that's going to be something that we are going to use to determine whether or not we should be doing depth testing and dealing with our attachments and so forth. So I'm going to go to the C file and just swap out this real quick, just so that's updated. Okay, and thankfully the number of changes in here is actually pretty small. So we have those two. One of the first changes that we're going to make is down here for depth and stencil testing. We're only going to do this if depth test is enabled, right? Otherwise, we're not even going to bother building this structure, okay? Which means further down, we're going to have to make a change to support that as well. But here's the reason that we're adding stride, right? Because right now, stride assumes a vertex 3D, and we're actually going to be dealing with two-dimensional vertices, which don't have as much data, right? So instead of hard coding this size here, we're just going to use stride, okay? So that's that. And then down here in the pipeline create info, right here where we're attaching depth stencil, we actually are going to conditionally attach that if depth test is enabled. And I think I actually moved that into a scope that I should not have. Yes, I did. The structure itself needs to be built here. Okay. So this needs to be out here for scoping purposes, but we're not going to fill out the rest of it if we're not doing depth testing. Okay. And that is actually all the changes that we need to make to this, but we are going to need those changes, so it makes sense to make them now. So I guess that means we probably ought to start with the Vulkan material shader, right? And thankfully there are no interface changes here. The only things that we have to change are really around the pipeline itself. And so let's go ahead and go to where this error is. So we have our main render pass, and then we have we need to pass the size of a vertex 3D for the stride, right? And then for the last boolean there, which is our depth test enabled, in this case it's going to wind up being true. Okay, so that is that. One other thing that we need to change is right now this global uniform object is in our render types INL, and this is pretty specific to Vulkan, so it actually really doesn't belong here, right? Because the renderer front end is not going to be concerned with this. So we're actually going to move this, and I'm going to go over to Vulkan types INL, right above the Vulkan material shader. I'm going to paste both of these, okay? And so we have our global uniform object, which is for our global uniforms for our material shader, and then we have the material uniform object, which is for the object level uniforms for our material shader. Which means these aren't quite descriptive enough, and these should probably be renamed. So I'm going to go ahead and do that now. And I'm going to rename global uniform object to Vulkan material shader global UBO. Okay. And I'm going to do the same with uniform object. This material uniform object is now going to be named Vulkan material shader instance UBO, right? Because this is really a UBO describing a material instance. Okay. Those two things are moved and renamed to be a little bit more descriptive and indicative of how they're actually used. Okay, so now if we go back to the shader, we should see those changes updated here. We can also see in the update global state, the range has been set to that as well, so that should be fine. Next, we need to come down to our apply material. And for descriptor 0, we see here that these things have been updated. We also see that this has been updated, but this variable name here kind of stinks. So I'm going to rename this to instance UBO. Okay, and I'll just apply that. Get rid of this error mess here. Okay, and that's just a little bit more descriptive as to how it's used. I'm also going to get rid of this dead code here. So I'm just going to get rid of this to do because it's not really to do anymore. We are getting that from the material, right? So we have that. Okay, so that should go ahead and do it for the Vulkan material shader. All right, before we move on, we actually need to add a new math type because I've mentioned this a couple times, but we haven't actually added a type for it. And that is for 2D vertices. So all the way at the bottom here, we have a vertex 3D, which takes a 3-dimensional position and a 2-dimensional texture coordinate. In our UI, we're going to be using 2-dimensional coordinates, right? So this is a vector 2 instead of a vector 3. There's no need to be using vector 3s if we're just dealing with 2D. So that's how we're going to deal with that. So we have a new type for that. So now we can actually go into our shaders, and we're going to create a new file. We'll call it vulkanuishader.h. And you'll now see the reason that I'm saying this is the time to split this stuff apart, because this is almost exactly the same setup as our material shader, right? This is just one that is specifically set up to use with our UI, right? So it still actually deals with materials. It's just these materials will not have quite as many properties, or at least not use as many properties as our world materials, but we're still going to use the same materials, right? But everything else is pretty much almost exactly the same. And so what I'm going to do is I'm actually going to create a C file, okay? And I'm going to paste the whole thing because, like I said, it is pretty much the same thing. There are a couple of types in here that we need to define. So let's actually go and do that first, right? Because we don't actually have our Vulkan UI shader type for one thing. So before I explain the C file, let's go to our Vulkan types. And here we have our Vulkan material shader with our UBOs. And right below the material shader, but before the context, I'm going to paste a bunch of stuff. And again, this is going to be mostly similar to the way that the material shader is set up, right? So we have a stage count. It's going to be the same number of stages, same number of descriptors, same number of samplers, at least in this case it's going to be 1. Our max UI count is going to be 1024. Again, we need to make that configurable. We have an instance state for each individual object, material, I should say. We have our global UBO for our UI shader, our instance UBO for our UI shader, and then the UI shader itself, right? And this looks pretty much the same. In fact, I may wind up splitting this out into some sort of interface to hold this stuff instead, but for now, I'll leave it as is. Okay, so we have our different type for that. So let me go back to our Vulkan UI shader.c. Notice that all of a sudden all the errors are removed, right? Because we have everything that we need. So notable differences in here are our built-in shader name UI is built-in.ui shader. So that's the file that's going to be loaded for it. All this stuff is pretty much the same. The descriptors, all this stuff is all exactly the same right now. The one big difference is in our attributes. So our attributes, this is using a vector 2 now instead of a vector 3, and our VK format here is R32 G32 instead of also having the B32, right? So that is different. And when we initialize our graphics pipeline, we're passing the size of vertex 2D, and we're also saying that we do not want to do depth testing. Okay. Other than that, we go ahead and create our Vulkan buffer using our new type. All of our descriptor sets, our UBOs for the individual instances, all this stuff is pretty much exactly the same, minus type size differences, right? And you might be asking, why don't you just share the shader file? Well, the layout of the material shader is going to be changing quite a lot because we're going to be adding a lot more descriptors to it, a lot more samplers. And so it looks the same now, but it won't be the same going forward. So yeah, pretty much this is almost exactly the same code otherwise, okay? So feel free to do a diff against it if you want, but that is basically all there is to our UI shader. It looks like we do have one thing down here. I don't know why this is bleating about that. It might just be IntelliSense tripping over itself because I haven't built in a while. Okay, so what this means is in our Vulkan backend, actually, one more thing I forgot to do. Back in our Vulkan types, we also need to make a change to the context because right now we have our material shader. We need to add our UI shader right there, right? So that's just using our new type. Okay. So now if we go to Vulkan backend, you'll note here that this error has been cleared up, right? Because we now have a UI shader and the correct types to use for that. Now, that doesn't mean that we've actually included it, so we need to go up here and do that. Shaders, Vulkan UI shader, okay? So we need to come into our Vulkan backend and right where we're creating the first shader, which is right here, we need to load our second built-in shader, which is now going to be our Vulkan UI shader, right? So we call the create method on that, obviously fail if we get an error. And then likewise, since we are creating, that means we have to come down here and destroy, and right above the material destroy, we'll put our UI shader destroy. The next change that we need to make is actually in our C file. So in our Vulkan backend, right now we have this Vulkan render update global state, and this is no longer descriptive, right? We need to actually rename this to update global world state, right? So that we know sort of internally which render pass and shader that we're talking about. And with that change, we also need to add a second for our UI state, right? And that's not going to take as many parameters. All we need here is a projection and view matrix, and we might not even need the view matrix, and an I32 mode, which we also may or may not need. So now that we have that, we can go back into our back end here, and we need to go ahead and paste in our update for our UI state, right? And this looks, again, almost exactly the same as our material shader. We're just using the UI shader instead. So we set the, so we use the appropriate shader, set the projection and view matrices, other properties if needed, and then we go ahead and call the update global state on that particular shader. All right. So next, we'll also see that our begin render pass now is working. So we should be good on the back end, at least for, no, there is one more change we're gonna have to make. So we've added a number of new methods, and we've not so far added anything to the front end to actually tell it about these new methods, right? So the first thing that we need to do is actually modify our renderer backend to actually include function pointers that we can use. So we have our update global state. We need to rename this as well to update global world state, okay? And then similar to what we did before, we just need to paste in a new function pointer for global UI state. And then we also need function pointers for our begin and end render pass, which I'm actually going to put right here, right there, okay? And at least for right now, that's all we're going to add. We are going to have to come back to this and add a little bit more, but So the next order of business is in our renderer front end, we need to go ahead and make some modifications. So we'll start at the top. First, we need to store a couple of things in our state. Right now we have projection and view. Those are for the world. We need copies of those for the UI. So we'll add those. And we'll make a note here that this is for the world. Okay. We should also probably put a to-do in here that our camera starting position should be configurable, because it's not right now. And then we'll also go ahead and add some in for our projection and view. All right. And our projection in this case is going to use an orthographic view, right? Because it's 2D, it's not 3D, so we don't want perspective. We want to use a flat orthographic view. And you'll note here that I have this intentionally flipped on the y-axis. And that's because OpenGL and Vulkan by default, they render from bottom to top, right? So 0, 0 starts at bottom left and goes up. And for a UI, that's kind of the opposite of what we want, right? We want our coordinates to be sort of the top left and then working our way down. So one of the things that we need to flip to make that happen is in our orthographic projection matrix. And what I mean by flipped is we take the left, the right, the bottom, and the top. But you'll note here that, so you'll note here that 720 is the bottom and the top is 0, which is opposite of what you might expect, right? If you're thinking the other way around. And so just be aware of that. The other thing I want to do is these render begin frame and end frame, they're kind of pointless. They're only called internally. They're no longer called externally, so I actually want to clean those up and just put that logic in line. So I'll come back to that. The next thing that we'll do here is on the resize, we also need to create one more projection matrix, right? Because this one up here just defaults to 720p, but when the window resizes, we want to actually use the width and height from that resize. Okay, so we're just going to generate a new one whenever we resize the window, and then we'll call backend resized. Okay. Since we don't have our renderer begin frame here anymore, we need to call our backend, our state pointer backend begin frame manually. Okay, which looks like this. So we just use this method directly, which is what was being called before. So it just removes sort of one layer of indirection there. So we call that, and then before we update the global world state, we need to begin the world render pass, right? So this is what I was talking about. It's an extra step. So you begin frame, and then you begin the world render pass, right? And we do that by calling the backend begin render pass and passing built-in render pass world, right? And this is that ID I was talking about. If for some reason that fails, we bleat about it and return false. Then we can go ahead and update our world state, right? And from here, we can go ahead and draw our geometries, right? And after we draw our geometries, before we call the end frame, we're going to go ahead and end the world render pass, right? Just by calling backend and world end render pass, and then passing the render pass world ID again. Okay, and so we begin the world pass. We begin the render pass here, update our global state, draw, end render pass. That's the general flow of render passes, right? It's pretty much the same thing we had before, except now it's a little bit more explicit in our layout. Okay, so this time, before we end the frame, we actually want to start our UI render pass, right? And we're going to go ahead also and update our global UI state, right? So we begin our render pass using this, and we update our state, okay? We're also going to draw geometry for any geometry that's passed in. We'll need to update our packet because we're going to have UI geometry passed in that. We don't have that yet, so we'll have to come back to that. And then go ahead and end the render pass, okay? And that actually should be pretty much it as far as the front end. There actually is one more thing we're going to have to do with geometry, but first and foremost, we need to go back to our renderer types for a second. And I'm actually just going to cheat and click this in F12. And so to our render packet, we have our geometry count and our geometries, but we need to add UI geometry count and UI geometries. And that's what we're going to use to actually draw those UI geometries, right? And so with that, let's go back to our front end, and we'll see here that that is all set up and ready to go. Okay, so application. Application, thankfully, does not take a whole heck of a lot of changes. So the only thing we're going to do in our application is right where we're calling our frame to be rendered, which is right here, where we're filling out our render packet. We're going to set packet.UI geometry count equal to 0, right? And then packet.UI geometries also to 0, okay? And this will just make sure that that loop inside works and doesn't really do anything, but we can go ahead and fill this out later, right? So we're not going to draw anything for now, but it'll at least allow us, or should at least allow us, to use that render pass, okay? So I'm going to go ahead and build. And it looks like I have some sort of warning I need to address. Yep, a couple things. So I missed one thing in the front end. I know what this one's about. This end frame right here, that needs to be replaced as well. So we're going to replace this with the logic that used to be in renderer end frame. So we call the state pointer backend end frame, passing the delta time, of course, and then we increment our backend frame number. Okay, so that was that. Let me go ahead and see. Let me build this one more time. Okay, that time it built without warnings, but let me scroll up and see what that warning was. Oh, it was complaining about the same thing. Okay, so we should be good to go. However, I'm not going to run yet because we've created the shader in code, but we've not actually created the shader asset to be compiled, right? So we actually need to go ahead and handle that. So before we do that, there is one tiny thing I want to do with the existing ones. We're actually saying that we require this extension, and that is not true. I don't remember the reason that I included that, but it's not true and it hasn't been true for a while, so I'm just going to remove that line. Okay. And then we are going to create a new file, call it builtin.uishader.frag.glsl. And for now, it's going to look remarkably similar to the fragment shader that is used in our material shader, right? It's pretty much the same thing, okay? However, our vertex shader will be a little bit different. So first, let's go ahead and create the file. And we'll call this builtin.uishader.vert.glsl, okay? And the vertex shader is also mostly the same, but there is one important change in here. We are going to flip the Y texture coordinate in this case, because our orthographic matrix flipping it actually makes the cube render upside down. And so by doing this, we're actually straightening the texture to appear right side up, okay? So that's kind of an important little thing here, to where before we pass the texture coordinate to the fragment shader to be used, we make this flip. Now we could have made this change in the fragment shader, but then you would have been running that calculation for every fragment as opposed to every vertex, so it's more efficient to do it here. Okay, so with that, let's go ahead and post build. And actually, I need to update this because it does not include our new files. So it's good that I caught that. So I'll do postbuild.bat first. And basically we're going to use almost the exact same thing that's up here, just using UI shader instead, okay? Since I'm here, I'll go ahead and do the bash file as well. So go ahead and paste this in. And again, same thing as before, it's just using the UI shader instead. So now let me go ahead and run post build again. And now we see all 4 of our shaders are compiled, right? And if we go up here, we can see that they're all compiled here, right? Perfect. So let's go ahead and run now. And it looks like for some reason, okay. I know what we forgot to do. So begin render pass is 0 because we did not actually update our function pointers. We did not hook up our function pointers. So it does not know what it actually needs to call, which makes sense. So we need to go to renderer backend.c. That would be this guy. And we need to add 3 things. So we've done our update world state. We need to do our update UI state. And then we also need to add below end frame our begin render pass and end render pass, right? And hook those up to the appropriate functions. Likewise, we need to make the update to this section down here. So there is that. So let's go ahead and rebuild. So now those function pointers should be hooked up and we should be able to run. And there we are. So that's a heck of a lot of work to have no visible change, but the visible part will definitely be in the next video. So what I want to do really quickly is show you guys something that I use to sort of prove that we are actually doing this the way that we think we are. So I'm going to use a program called RenderDoc, and this is by far not a tutorial on how to use RenderDoc, but it allows me to sort of visualize and debug various shader issues and just graphics pipeline issues that might occur along the way. So you guys will probably see me pop this up on the screen from time to time. But what we're looking at here is we want the launch application tab. We're going to point it to our executable, and this is going to attach itself to that. Oops. If I get the path right, which that should be code bin. And so it's attached itself. It also puts a nice little FPS counter there for us and gives us a little bit of information. And it says we're using Vulkan F12 print screen to capture, right? And that's actually what we want to do. So I'm going to hit F12 to capture, and then I'm going to exit the application. Okay. So it goes ahead and saves that snapshot and loads it up when I exit the application. It allows us to actually look at the individual pixel colors on the output image. But what we're interested in is actually going to be over here. So this is what the entire frame looks like. These are all the calls that we make to Vulkan. And this gives you guys a kind of an idea of how all this stuff comes together. Okay, and so what we see here, and I have a feeling that this, for some reason, this isn't actually displaying color pass number 2 for some reason. I'm not 100% sure why, but if we expand color pass 1, we'll see that we have a begin render pass right here, and then this is all our command by bind pipeline. These are actually our shader uses, so we still have way too many of those. We need to remove some of those. Here's our push constant, our bind descriptor sets, our vertex buffer, index buffer, draw. There's our draw call. And then we end the render pass. And then we have the next render pass, which is load. So this is our UI render pass. We bind the pipeline a couple of times. Again, we should really only be doing that once. We bind a descriptor set, which is the global descriptor set, but we're not actually drawing anything yet. And then we end the render pass, right? I have a feeling because there's no draws here, that's probably why it's not showing as color pass number 2. But you guys can kind of see the flow of an entire frame using this. So I would highly recommend that you guys download RenderDoc and use it to launch your application, play around with it, explore. There's lots of cool stuff in here. I don't even pretend to know how all this stuff works myself. I feel like I've only scratched the surface because there's that much that this tool gives you power to do. So anyway, with that all said, thank you guys so much for watching. I hope you guys are enjoying this series and learning a lot from it. Next time we're going to be rendering some geometry on our UI pass, and there's a couple changes we have to make to support that, but that is for the next video because this one's gone on long enough. So again, thank you guys so much for watching. If you liked the video, toss me a thumbs up. If you haven't already, consider subscribing. Hit the little bell icon there to get notifications as to when new videos in this or other series drops, and I'll see you guys next time.